Okay, so we have a stone tied to a spring and swung around in a vertical circle at constant speed. I don't know how you can achieve constant speed by swinging a stone using a string, because usually the stone will slow down when it's near the top, and you'll be going at faster speed at the bottom. But let's not argue with the question, huh? Okay, so what are the forces involved for this circular motion? Of course, there's the weight of the stone pulling it downward, and the weight is the same whether you are at the top or the bottom position. It's still the same pull by the earth. Of course, it's tied to the string, and the string is stretched, so the string will be pulling inwards. This is a circular motion, and this is a circle, so we know the direction of the centripetal force is towards the center of the circle. So when it's at the bottom, the centripetal acceleration is up. When it's at the top, the centripetal direction is down. And because they say it's going around at a constant speed, the centripetal acceleration is also the same in magnitude whether you are top or bottom. So the last force involved is of course the tension of the string. So let's talk about the bottom position first. When it's at the bottom, the string is here, the string is stretched, so a stretched string always pulls inwards. So this string is going to pull the stone upward. Let's call this T. And we know the net force is in the upward direction, right? So when you're at the bottom, the net force is the tension, which is in the centripetal direction, minus mg, which is in the opposite direction, and this should be equals to m r omega square. This is just the required centripetal force, which means the tension can be written as mg plus mr omega square. When the stone is at the top, now the string will be here, right? Again, the string is stretched, so a stretched string always pull inwards, so the string is going to pull the stone downward. So when you're at the top, both the tension and the gravitational force is in the centripetal direction. That's why we add the two of them up and we equate it to the required centripetal force. So when you're at the top, the tension, let me put a subscript here maybe. Oh, sorry, this is bottom and this is the top. So when you're at the top, the required centripetal force is mr omega square minus mg. That's why you see the tension is always strongest when it's at the bottom, because the tension, which must provide the required centripetal force, must also overcome the weight, which is pulling in the opposite directions. So the difference in the magnitude of the tension when it's at the bottom and at the top will simply be, maybe I'll write this as mr omega square plus mg, minus when it's at the top, which is mr omega square minus mg, and the difference is simply 2mg. This 2mg comes about simply because when you're at the bottom, the weight is working against the tension, and when you're at the top, the weight is helping the tension to provide the required centripetal force. Okay, ta-ta!